Let us continue our discussion on bases. In particular, we'll talk about orthogonal bases. Given a basis, it allows us to define the subspace. For the subspace, in this example, W is defined by linear combinations of column vectors that belongs to the basis. And the basis is nothing but a set of independent column vectors in Rn in this example. What it also means is that any column vectors that spans the space can be the basis of choice. However, among all the vectors that are available to us, we like the orthogonal set the most. So when we have an orthogonal set, we call them the orthogonal basis that spans the space, and we like them very much because it is much nicer to use them, as it allows us to compute the weights of the linear combination most easily. Let us use the following example. Y is an element of W, and W is a subspace of Rn. The basis for W is made up of P column vectors U1, U2 up to UP. Let's remind ourselves, each of these column vectors is Rn, n-dimensional vectors. Given that we have U1 to UP arranged as a matrix, so technically this is a n by P matrix. To form linear combinations of it, we can use matrix vector multiplication C1, C2 to Cp, where C1 will be multiplying with U1, C2 multiplying with U2, and so on. This matrix vector multiplication is represented by this equation here. And hence, we can also write y is equals to the expression on the right. Once you have reached this point, you'll realize that this is our system of linear equation, and we can solve for y by finding the inverse of this matrix over here. I'll now clean up and rewrite the equation like this: y equals to uc, where u contains the column of u1 to up. Therefore, to find c, what we do is that we multiply both the left hand side by u minus 1, which is the inverse of u, now if this works, if u is a square matrix, and this will work because u columns of u are independent, then we can find c. In the case when u is a rectangle matrix, because now what we have is u is a n by p matrix, then u minus the inverse of u does not exist. But later on, you'll realize that we use something else called the pseudo-inverse. Nevertheless, this whole issues of doing this to solve for c is computationally expensive. Now, what happened is that in the case when the columns of u are orthogonal, we have shown in the previous lecture that Cj can be easily computed by having this equation multiplying by Cj on the left hand side, sorry, not Cj, Uj on the left hand side and Uj on the right hand side, dot product, and what you'll realize is that it will reduce to the following equation because Uj is orthogonal to all U except Uj, cancelling all the elements except Cj, Uj. What it means is that all we need to do is to perform y dot uj divided by uj dot uj for j equals to 1 to p, and we have found all the weights of C. This is a computationally cheap way to find the coefficients of C, the weights that forms the linear combinations using with U to form Y. In the next slide, we have S, which is a matrix containing 3 column vectors, and these 3 column vectors are orthogonal, and therefore S is an orthogonal basis. The problem we want to do is we want to represent Y decomposed by S to find the weights. So what we are doing is Y equals to SC, and we want to find the coefficient C. It is clear that C1 is 6, C2 is 1, C3 is minus 8 just by visual inspection. There is a minus 8 in this entry over here. In this standard basis, we have solved the problems of finding C just simply by visual inspection. But if we have followed the previous equations in the last slides of finding C in this manner, the answer would have been the same. As a last example, we have 3 column vectors u1, u2, u3. First, in this example, we show that u1 dot u2 is orthogonal, u1 dot u3 is orthogonal, u2 dot u3 is orthogonal, and therefore these 3 column vectors forms an orthogonal set. We use this S to represent the column space. We want to express vector Y as a linear combination of vectors in S. Using what we know, since u1, u2, u3 are orthogonal, what we can do to find the coefficients of C1, C2, and C3 is simply first calculating the dot product between Y and u1, u1 dot u1, and we divide it. We'll have C1 equals to 11 divided by 11, and we have 1 over here. For C2, we again find y dot u2, and we divide it by u2 dot u2, and the answer is minus 12 over 6 over here, which is minus 2. So this is C2. And for the last one, in C3's case, y dot u3 divided by u3 dot u3 is equals to minus 33 divided by 33 divided by 2, and we get answer minus 2. Do it by yourself. Evaluate u1 minus 2u2 minus 3u3 to prove to yourself that will give you the value of y, which is 6, 1, and minus 8. This concludes our discussion of 6.2.3 orthogonal sets and bases.